Okay, so for this exercise, we're going to be looking at determining the sequence or the series of Fibonacci numbers, which are found in sciences quite a bit and in nature quite a bit. So the Fibonacci sequence is sort of recursively defined, and it's going to lend itself really well to a recursive solution as well. So the idea behind the sequence is that there's a base case. The first two numbers in the Fibonacci sequence are 1. So 1 and 1. And then the next value, and from there on in, is the sum of the previous two values. So sort of sketching this out, if we have, we have our initial values, 1 and 1. The next value is the sum of 2 and 1, or 1 and 1, so it's 2. The next value is the sum of the previous two, so it's 3. The next value is the sum of the last two, so it's 5. And then the sum of 3 and 5 and 8. And you can sort of get the idea of what's going on here. So we immediately have sort of this definition where each individual, if I was to figure out what was the 8th Fibonacci number, right? You can define that as, well, that's easy. It's the 7th fib plus the 6th, right? And then if you want to ask, well, that's great, but I got to figure out what the 7th Fibonacci number is. Well, that in itself is the 6th plus the 5th. And the 6th is the 5th plus the 4th. And this one is the 4th plus the 3rd. If I was looking at the third one, and I'd have to carry this all the way down here, but I'm going to try to end this recursive sequence out here. This would be the sum of the second and the first. Right? The second and the first are just 1. That's the base case. Computing 1 plus 1 will give me the third number. That'll give me 2. And that'll cascade all the way up, just like a regular recursive function call. Right? So we've got our base case, Fibonacci 0, Fibonacci 1, the first and the second values in the sequence will be 1 by definition, and the rest of them will be recursively defined as the sum of Fibonacci of n minus 1 and Fibonacci of n minus 2. Okay, so let's give this a shot. So let's ask the user, let's say the user is going to tell me which Fibonacci number they want. So we can say input, enter n for the nth Fibonacci number. And I'm going to call a function. Right, I'm going to make some room for it up here, but I'm going to call a function n equals fib of, well, actually that's answer equals fib of n. And then I'll just print out the value. And I'll use string concatenation here. And print out the answer. Okay, so there's my function, and there's my main part, and let's write the actual function. So as we said, there's a base case. If n is 0 or if n is 1, this fib function is being asked for the first or the second Fibonacci number. So I'm going to check that. If I'm going to say if n is less than or equal to 1, I know the answer. It's just 1. Otherwise, the answer is fib of n minus 1 plus fib of n minus 2. That's what I'm going to return. Okay, so let's see if that works, and then let's kind of investigate a little bit more about how it's working too. So let's type in 8. Right? The 8th Fibonacci number is 34. And if I bring over my test case right here, I get 0, 1, 2, 3, 4, 5, 6, 7, 8, right? It's actually the ninth number in the sequence, but I'm starting at 0, right? So that's good. That's making sense. So what I want to start to look at is, how is this really working, and how much computational effort is um, actually being done. So let's do maybe 25. All right. Well, that returns pretty quickly. 100, and this is starting to take a lot of time now. You'll notice that this is going to run for a pretty good chunk of time, and I want to kind of just think a little bit about why that is. Why is this algorithm not particularly efficient for large numbers of Fibonacci number, or large ends of the Fibonacci sequence? And it comes back to what we were drawing here. Let me go back in time here so I have a little bit more room. And I want to just point out all the wasted computation. This is still going, by the way. So if I'm going to do the Fibonacci number of, let's say, 8, right, well, that's going to be broken down into fib of 7 and fib of 6, right? N minus 1 and n minus 2. This is going to be solved by doing fib of 6 and fib of 5, and this is going to be fib of 5 and fib of 4. And keeping going with this, and I've got, I think, some time to kill because this still hasn't finished, we start to see some patterns emerge here. I'm going to run out of room eventually. And the pattern that I'm looking at here is, how many times has the fifth Fibonacci number actually been calculated? It's been calculated once, twice, 3 times. The answer is the same each time, right? And of course, this is going to cascade down. This fib of 5 is going to go to fib 4, fib 3. That's going to go to fib 3 and fib 2. If we count how many times, fib 3 is going to be called, 1, 2, 3. It's going to be called here. It's going to be called here on fib 4 and directly on fib 3. It's going to be called over here 1, 2, 3, 4, 5, 6, 7 times. So what you're seeing is that the recursive definition, the code itself, is very, very simple, and it's very close to what the problem description actually is. But in reality, we're doing a lot of effort, right? We're actually computing the answer for the same question multiple times, and this is just fib 8. When we do fib of 100, we start to get extremely long run times, so long that I'm not going to bother waiting for this at this point. All right, so I'm just going to kill it, and we can see that it was pretty busy. By the way, this is the call stack, and we can see all the functions that have been called. And this is only a very small slice of them. So it turns out that you can actually you can calculate the Fibonacci sequence iteratively as well. Iteratively meaning just in the same function, well, one function just goes around a loop. And all we need to do is sort of remember a history of the last 2 values being created. So I'm going to write that code. We're going to call it fib iterative, and it'll take n as a parameter. And for this, I'm going to remember 2 values, right? So we know that the first number, n0, is 1. We know that the second number is 1. And now I'm going to create a total, which is going to be an accumulation of my values. Oops, actually, I don't think I need that. Let's go for our for loop first. So I'm going to go for int I, or for I in a range from 2 to n. Right, So n might be 5, right? And if n is 5, we know the first two, and now we're going to calculate the third, the fourth, and the fifth. If n is actually 2 already, or maybe if it's 1, this for loop might not go around at all. And each turn around this for loop, I'm just going to increment my total. All right, I'm going to carry along my value. So t, which represents the value that was current right now, so the last value I've computed. I'm going to set n1 to be equal to n1, the previous n1, plus n0. And then n0, it's kind of a trailing indicator here, that'll be equal to t, or the old n1. Right? So I'm just computing a sequence of numbers, and I'm making n1 equal to whatever n1 plus no currently is, and then I'm making no equal to be what n1 was. Right? So if we want to kind of sketch this out, let me rewind here. We've started with n1 is equal to 1, n0 is equal to 1, and let's say I'm calculating the fib of 4. Right, so I'm going around, and when I is equal to 2, I'm going to have a t value equal to the n1 from my code. I'm going to have an n1 value equal to the 1 plus n0. And I'm going to have an no value now equal to t. T is just a temporary variable. Notice that n1 now is the newest fib2. It's the third Fibonacci number. Now I is equal to 3, so I'm keep going around that for loop, and I'm going to do the same thing again. Right? So I'm taking 2 and I'm putting it into t. I'm taking n1 and I'm making it now 3, the sum of 2 and 1, and now I'm moving this 2 into no. And the Fibonacci, the third Fibonacci, or fourth Fibonacci number, Fibonacci of n3, is equal to 3. When I is equal to 4, I'm doing the exact same thing again. This is 3, this goes to 5, and then this goes to 3. All right, so that's all my code is doing. It's just kind of keeping it's keeping track of the last two previous numbers. At the end, when my for loop stops, I'm going to return n1 plus no. So first off, I want to see answer iterative, and I want to make sure that it actually works. So let's print out both values. And we'll just do a small number. Okay, so fib10 is 89, that looks good. I think we did 8, right? That was 34, so that looks good. So let's use a timer. All right, so we can import time, which is a package that will allow us to keep track of a high resolution of time and find out what time it is, essentially, with a high resolution. And before we call these, let's actually figure out what time it is. So time.time will return the number of in seconds, and it's pretty high resolution. And we'll say recursive time is equal to time.time, the current time, minus the start time. Right? So I've calculated the Fibonacci sequence, and now I'm figuring out how much time it took me. And now I'll do start equals time.time again, and I'll do iterative time. And let's print out how much time it took. And we'll print out the iterative time too. Okay, run that. And you know, we wouldn't imagine there's a dramatic difference, but by the way, it's already 6 times slower, the Fibonacci of 8. Let's do the 30th value. Right, so Fibonacci of 30, the 30th Fibonacci number actually took over a second, where this is 1.57 times 10 to the negative fifth seconds. The difference is clearly very dramatic. So I kind of hesitate to show you that to that performance benefit or that performance difference, because it's easy to get the idea that, you know, maybe recursion is just always terrible, and it's not true. Recursion was very, very good for doing bisection. Recursion, we'll see, was very good for binary search. Recursion is great when it really is effectively splitting the problem in half or close to in half as each turn around a loop goes. But there are a lot of examples where recursion looks very simple but ends up being kind of catastrophic. And this is one of those situations. And the reason being with this is that we're actually going through, we're calculating each Fibonacci number many times along the way. And so we're wasting a fair number of time. Looks like 50 isn't going to finish in a reasonable period. It's probably been at least 20 seconds or so. I'm going to assume that that's pretty long. Let's try 40. Let's see if that only takes a few seconds. And again, through some video editing magic, we didn't actually wait 107 seconds, but I did wait for this thing to finish. So it took well over a minute to compute the Fibonacci number 40 using the recursive algorithm. I got the same exact answer for the iterative solution, but well, we're still 1.6 times 10 to the negative fifth seconds. So that probably closes the book on the Fibonacci recursion scenario. Keep that in mind. If you do use recursion, you should certainly test the performance for numbers as they get a little larger. Keep your eye out on them. If it's starting to get too slow, remember that anything that you can do with recursion, you can do iteratively. And in most situations, it's going to be quite a bit faster.